Okay, morning class. It's about the time. Let's start today's discussion. So we're going to start a new chapter today, and that's quite exciting for me because we're going to talk about something go beyond just the model and confirmation, etc. We're going to talk about something really important is polymer solutions. There's 2-3 areas you're going to use polymers processing extensively. You can imagine you will need to process a polymer in solution state. That's one of the big area of engineering plastics. The other is polymer melt. So we're not going to talk too much about melt, but this is going to cover everything you need to know about polymer solution, polymer formulation. So let's first talk about what we're going to discuss for the whole chapter. So throughout the chapter, what we're going to cover. We're going to talk about several important parts in this chapter. This will cover an important theory, and it's called Flory-Hagen theory. So for those who have not heard about that, this is a theory that can help you to predict if the polymer solution will be able to mix or not. So if the polymer will be dissolved, or if two polymer melt will be able to phase mix without phase separation. Why this is important? Because almost every single plastics you are holding or using is more or less reasonably homogeneously mixed. Because if you have phase separation, you're going to have inhomogeneity in different parts of your component. And that's not ideal. That's not what we want. So a lot of time you will learn that it's very important to make homogeneous polymer with additive, etc. Another part that is quite important is talk about polymer solution here. We also need to learn about at what concentration your polymer might be able to phase separate. And for those who have not learned about this term, phase separation basically means you have two material might be mixed, but they could be phase separated. So in a solution is let's talk a little bit about this part, phase separation, etc. So a solution is a homogeneous thermodynamic state where the solute is distributed evenly in the solution. So this is an example when you have, let's say, dissolve a polystyrene toluene at low concentration. You can see a transparent solutions. Or coffee would be another example. It's uniformly dispersed. It's everywhere is similar concentration. But once you start to add things that would phase separate, example would be if you mix oil in water, and when you stir them, they can temporarily mix. But if you let this sit a long time, they will phase separate into two later. So phase separation also happens quite a lot, happens in polymer. A great example is when you mix polymer blends, they are not likely to phase mix. Use plastic recycling as an example. One of the challenges that people face now is people use mechanical recycling, which means you get the plastics, you chop them down, and you start to mix them, and you do extrusion. So in the ideal case, you want them to be one single component, uniform everywhere. But in many cases, you will see it might look like to your eye it's relatively, on macro scale, it's okay, but at nano scale, they actually have phase separation. And this is one of the problems that for plastic industry, they need spend a lot of money sorting them out. So you need to sort out polyethylenes, polystyrenes, and you need to spend a lot of time. So that's why polymer solution is important, where we're going to talk about how you can learn from this class so that you can apply what you have learned to formulate your polymer solution that can be phasely mixed and no phase separation. Or in the case if you want them to phase separate, you can also design the solutions to have that property. So We want to cover two theories. So today we only going to review some of the thermodynamics. And how many of you have taken thermodynamic class? We have 3. Okay, we have half of the class roughly. So we're going to do a review of that. We will talk about thermodynamic concept like free energy, enthalpy, entropy, those concepts first. It's going to be a refresh for everybody to learn what those concepts are. And then we will have a discussion about a topic related to solution theory. Okay, so solution mixing theory. So this would be, one of the topic what we're going to cover. Then we will cover Flory-Hagen theory. So these are two of the theories you will be able to predict if you pour two solvents or you pour two polymers, will they mix or not. So in the top one, we mostly concern solvents mixture because it serves as a basics for when we talk about Flory-Hagen theory. This can be polymer-solvent mixture, or you can have the polymer-polymer case, where you have polymer and polymer in blends, and you can understand if they will mix or not. So that will cover probably one for each week. Then after that, we will discuss about osmotic pressure. For now, you don't need to know more than the name, but osmotic pressure is an important phenomenon, help you to understand thermodynamics. It's a pressure that arises when you mix polymer solutions. When you put a membrane in between, they will have a pressure difference. So we will discuss about that. It's very much related to Flory-Hagen theory in solution mixing. Okay. After that, we will have a topic focusing on what is Flory-Hagen's parameter. So this will be important. We call it chi parameter. It's not x, but it's a Greek version of x. So this parameter is very crucial throughout the lecture. You guys will learn what is Flory-Hagen's parameter and how can we study and measure it. And last but not least, we need to find a way to calculate and understand how to predict a chi. So the very last portion of the lecture, we're going to talk about chi prediction based on solubility parameter. So by the end of the lecture, you should be able to predict the chi parameter, okay? And why that's so useful, because once you know the chi, you can adapt to Flory-Hagen theory, and you should be able to predict if the polymer and solvent will be dissolved or mixing or not. You can choose any two. So if you made a new polymer, you are not sure if it will be soluble or soluble at what concentration. You can apply this basically theory to calculate. Okay? You could also calculate what if you have a melt. You have mixing polystyrene or polyethylene. At what molecular weight they are potentially soluble, and at what molecular weight they are not soluble or mixing with each other in that case. And at what mixing ratio, because mixing ratio matters here as well. And obviously, it will make an impact on polymerization. Why? What we have talked about solution behavior is important. Imagine you polymerize a polymer in solution. A very common problem in polymerization is that you will have polymer precipitated out when the polymerization goes on. At low molecular weight, a lot of polymer are soluble, but at high molecular weight, they actually refuse to stay in solution. They want to precipitate out. And we will explain to you guys why that's the case, and we will discuss how based on this class, you can show the polymer chemist how to better optimize their polymerizing condition. Polymer product design, of course, that makes sense. Every single product nowadays in plastics, it's a blessing and a curse in a sense that none of them are made of a single component. So even look at this pen, looks like just one white plastics. It actually has tons of components comes into it. Plastics will be the majority, and this could be polypropylene or polyethylene, but it added a lot of components. Like the color comes from a filler. You also have lubricant when you need to inject it. They also add a lot of those antioxidants, so make it not UV oxidizable. So all these components, when you design the product, you throw a lot of things. And you don't want, outcome is they come up with part of it, just don't mix with the rest of the polymer. That will be disastrous, and you don't have one product. You have one bad product and a lot of byproduct, right? So it's important you understand what is, for example, the capacity they can load any other fillers. And in the case where you will need multiple polymers, you would also co-extrude them. In that case, it's even more important because now you have two polymers, and the majority of them will be polymer. And if they don't phase mix, they will have phase separation problem. Okay? And polymer characterization, we will also talk a little bit about that. And that's related to osmotic pressure, the last part. We will talk about how thermodynamics can help you guys understand how to characterize a polymer. So if we look at here, one of the useful part is osmotic pressure can actually predict the solvent-polymer interaction strength. So you can use, based on measuring osmotic pressure, you can do two things. It can tell you the molecular weight of your polymer. As simple as that. You can use that instead of light scattering to measure molecular weight. Although this is a little bit outdated, so because light scattering is so simple, most of people don't use it, but they can actually also work. Then they can measure secondary coefficient. So this is a parameter that can tell you if your polymer is dissolving in good solvent or bad solvent, depends on what this parameter. So as you can see, we're going from very fundamental to very applied. Gonna be in the second month of this lecture. And we're going to go through all these in the next month or so. And we will try to finish everything by the end of October. And we will have wrap up the chapter the textbook would be chapter 7. If you haven't read that chapter, it's very well written. You should go back and take a look. Okay, any question about arrangement, like the length of lecture, what we're going to cover? And my expected learning goal is you guys need to able to explain to your peer or your future employee what these concepts are conceptually. Make sure you understand those different theory. And practically, in the end, you should be able to, based on prediction of chi and prediction of, let me write it, prediction of solution property. Okay, so this is quite important because, okay, so we need to learn all these. That's a goal for this. So we have to start with somewhere. So what we're going to start is first to introduce some of the basic thermodynamics. Basic thermodynamics. So the first idea we're going to introduce is called Gibbs free energy. Okay, that is written as the G. Gibbs free energy is basically the difference between the energy in the initial state and in the final state. So we can see this would be written as free energy of mixing delta G, free energy of mixing. So when we mix things, we could look at what is free energy where we start off, where we end, and minus where we have start off. So what is this free energy? So you can think about this is the energy the system that could obtain, so at a given time. If you have free energy is going down for the process, which means when you after you mix it, minus what you have start, if it's negative, that means you will have a spontaneous process. So which means your system likes to make things happen if it can drop free energy. Okay, so example would be if we have free energy where we start off, so this we would call G, where we start off is here at high value. So where we start and where we stop. If it's lower, if you can shed some free energy from initial to final, this process is favorite from the thermodynamic perspective. It's easy to understand if you have a rock, you can think about, it's like to roll downhill because you lose energy, and lose gravity energy in that sense where if it's losing it through the process. So make sure you understand that the final after mixing minor, where it starts, it needs to be smaller. And now, this part I need to spend a little bit of time explain. So how many of you heard, half of you I know already learned of enthalpy, okay? And half of you probably already know entropy. So let's explain the entropy first, because that's a little bit easy. Enthalpy and entropy are two thermodynamics terms. So entropy is related to the randomness of the system. So give me an example where in your life something is really organized. Or anyone?
Dresser.
Dresser, okay, good. I like it. And so let's use my dresser example. On Monday, I did my laundry over the weekend. I folded all my clothing. I ironed them. Okay, it didn't happen there. But I put it straight. Every single them. I even sorted by color. Okay, red goes to the left. Black goes to the right. Perfect. But then throughout the week, I wear that and then I get dirty. I throw in my laundry bag. So you can see the system start with something really older. And the entropy basically means that the randomness. And there is one unique aspect of entropy is entropy for the system, it's always one spontaneous goes up, which means your order will lost over time, unless you put some work into it. The example for my case would be my organized clothing will go to the laundry. In the laundry bag, nobody would fold it and clean it, like put it in the laundry. You just throw it, right? Does that make sense? Your randomness goes up. The other example would be, I have a 7-year and 3-year at a house. Well, my weekend job, it's a job, literally a job, is clean up the toy room. So I need to put everything back where they're supposed to be. And I put a lot of work into that. So the randomness, the toy wouldn't spontaneously go back where they are. So you need to reduce it if you want putting external work to it. In other words, everything will be spontaneously become random. So our body is actually another example. It's in order because every molecule is organized in a certain way. And when you pass away, you didn't put any energy because you don't take food. Everything will dissipate, okay? Disappear back to nature. So that's another example. So in the thermodynamics, when we think about mixing polymer, entropy is actually a very important part because when you mix solvent, when you mix polymer, you change the entropy, and very dramatically. you will change a lot of entropy when you start to mix in things. And we will, when we teach about that, we will talk about the entropy part specifically, okay? And then we have enthalpy. So what is enthalpy? Entropy is randomness. How about enthalpy? Enthalpy is related to the energy exchange. Particularly, we can think in the context of heat exchange. So a great example would be when you mix in some type of polymer, maybe acid and water, for example, sulfuric acid and water. Sulfuric acid is corrosive, so be very careful. But when you mix them, in the basic chemistry class, some of you might have did it, you will see that when you mix them, it's an exothermic process, which means it gives out heat. So your beaker, the water will heat up. So this process is basically means the process involves giving out the heat. There's also process intakes the heat. Example would be crystallization. When melt happens, not crystal. When melts happens, you typically take up the heat. A great example would be, when you have snow melt, it's all intake or give out heat in that process. So that's what enthalpy is. Enthalpy is related to heat exchange. So when you mix polymer together, depends on the interaction of different polymer. They might intake heat, they might give out heat. Just depends on what pair you put together. Make sense? We will talk about specific case when we discuss about. But for now, it's a refreshment for you guys to understand what enthalpy is related to the heat exchange. Entropy is related to the randomness of the system. And delta G, the Gibbs free energy, is related to delta H minus T delta S. So delta S is entropy we have talked about. So T here is just the temperature. It's the temperature where your system sits at. Entropy is related to the temperature, so it's always T times delta S. T is usually given in the units of Kelvin. And for those who are not fully familiar with it, so we have several systems in the US. We have Fahrenheit, we have Celsius, and we have Kelvin. So for those two, 0 Kelvin is absolute 0. You can't reach that. So it's about, if I'm not mistaken, 233 degrees C. At room temperature, we are at the 0 degrees Celsius, we are at 273 Kelvin. Okay? So we have this relationship. So when you calculate the Gibbs free energy, make sure you use K, not Celsius, because otherwise you will have problem. You potentially could flip sign. That could never happen. So delta. This is basically many years of discovery. People define this thermodynamics. Delta H minus Ts will give you the free energy. So you can tell that because T is always a positive number, so when entropy goes up, your delta G will go down, right? So when delta S randomness increases throughout the process, T times a positive value is a negative value. So assuming you don't have any exchange of delta H, your delta G will become a negative value. So that's favor, right? We talked about delta G drop is what the system wants. And system prefers the process. So in other words, thermodynamically, everything should become more and more random. That happens in my toy room, thermodynamically. I can't fight the physics law because it just wants to be more random. This also goes on to your yard. If you have a yard, if you need to do yard work, otherwise your weeds start to grow, you need to cut your grass, etc. It's another example that your randomness will go up, back to nature. So now enthalpy. Enthalpy means the heat exchange. So giving out the heat is always spontaneously. So give out heat means you lose heat, so delta H will be minus throughout the process. So if you have a process that gives out heat, that will be, and entropy goes up, that's duly favored by thermodynamics. That means you can make it and it will definitely happen. Okay? Any questions so far? Yeah, pretty simple. So then let's think about another example when you mix in two different material, two substances, mix into a solution. So the Gibbs free energy for the processing of mixing must be negative. So what does that mean? So when you mix two items together, so let's talk about, use this as the example. I have a beaker of toluene. In this box, I have a box of hexane. So if I have a bigger beaker, let's call it 1 liter, 1 liter. I have a 2 liter. I both dump them in there. It could possibly have two outcomes, right? You have option 1, you would have a homogeneous mix that, they mix together. The option 2 would be you have a layer of toluene probably in the bottom because it's heavier. You have a layer of hexane. So how do you predict if this option 1 will happen or option 2 will happen? That's the goal of the whole lecture of this chapter. We just need to calculate what is the delta G in mixing. Okay? So if the delta G on the mixing process is negative, that means throughout mixing we're going to lose some free energy. The Mother Nature says, let's do it. I like it. Let's make that happen. However, if you, throughout the mixing, if you have delta G M mix is positive, that means it's unfavorable. That means you would have this case. They refuse to mix. They just form an interface, and they would have phase separate into 2 layers. What happened? Oh, question.
I've got a problem about that. What happens if we get to 0?
That's a good question. That means it won't have any energy gain. So I would think they will not phase mix unless it's go down. Okay? Because before and after mixing, or they could be, depends on the condition, they might be mixed if you stir them because they don't have the force drive them to phase separate. Does that make sense? It won't stay wherever the condition it is. It's only want to phase separate because it's one minimize the interface and let them phase separate. So now the question for the next 2 weeks we're going to answer is, how do we calculate this delta G? If I can computer, I can plug in the number, then I can give you the delta G, then even my kids in the elementary second grade will tell the answer because, right? It's basically 2 conditions. But that's where the hard is, how do we get the delta G? And we're gonna actually discuss in the 2 contexts. We're going to discuss in the context of understand what is delta H. So what happens when you mix 2 things? What happens to the delta H? So I want to ask you guys, how many of you think delta G might go up? How many you think of delta G might go down when you mix in things? Delta H, sorry, I said that incorrectly. So when I mix, let's use this example, toluene hexane. Will delta H go up or go down?
I think it only goes up if there's a reaction.
That depends.
If there's an exothermic reaction.
Yes, so that depends specifically then how the molecular interacted with each other. So some molecular, they're besties. They just like to hang out with each other. Of course they will be exothermic to promote, right? Some of them, they just hate to see each other, don't want to even talk to each other or have eye contact. It happens in some type of molecular, they just don't mix, okay? So delta H will depend the molecular pair, and we will discuss in more detail. And you will learn a way to calculate delta H. Delta H actually is related to chi. And it will take a couple lectures before we get there. So how about delta S in the mixing? Will it be positive or negative?
Won't delta S be positive since you're mixing two things together?
Yes.
Separate before?
Yes. Good answer. So could it be delta S go down while we mix them? I saw a lot of people shaking hand. No, right? Because the randomness always goes up when you mix in things. So delta S, you will learn throughout the lecture, delta S always is got promoted by mixing process. So no matter how you mix one into the matrix or mixing, 50-50, it's just always going to increase the randomness of the system. We're going to get into that. Okay? So any questions so far before we move on? All right. All right. This is a little bit busy slides, but just stay here. We're going to introduce another idea, which is related to this partial molar factor. So in the two-component system, if we have Na moles, one mole is basically a measurement of how many molecules are there. So if we say this is Na, N is basically a constant or a number. If we have a certain amount of species A and M mole of species B, to conceptualize of these into the two pure components. So the delta G solution, delta G mixing, this part is still the same as this equation, but now we can think about each pure component because we have, before we mix, we have two components. We need to consider how much delta G that you had for molecular A and how much delta G you had in molecular B. And this is just mole. That's just how much free energy per mole, non-capitalized G. Okay? Why we have to consider everything per mole? Because we need to consider it in a unit cell. So in terms of mixing, how much molecular you have in mixing each other plays a big role. If you mix one molecular in its matrix versus if you have 50 fixed mixture, it's very different. You can understand that in the context that if you have two polymer, you want to mix them. If you have 10%, 90% mixture versus 37, 70 or 50-50 mixture, they will mix differently. If it doesn't mix 50-50, it doesn't mean that it cannot be mixed at 10-90%. Okay, it has a chance to be mixed at different ratio. So the mixing or not between two polymers will depend on how much ratio they're going to mix. And later you're going to learn that this ratio matters and quite a bit. And how do we calculate the ratio? It's typically use the molar volume or molar ratio. So if we have one polymer, two polymer, we don't talk about like weight fractions or volume fraction. A lot of time we talk about the molar fraction. The molar fraction is basically how much moles of a polymer, how much moles of B. Okay, I want to get it straight out there. All right, so this is where it's going to get a little bit tricky. So how many of you is still familiar with this partial derivative sign? So let me show you guys what partial derivative mean here. Just another refreshment. So if I have G equals to I'll give you a random number. Don't call it G. What do you want to guys call it? Y? How about Y? Equals to A times B plus C times D plus E times F. So partial derivative basically means this derivative, if I write here, if I derive A at a constant C, D, E, F, this operation means when I take a partial derivative. So if I take a derive of A, we can see Y is related to A, B, C, D, E, F, right? But when I say my C, D, E, F is constant, that means when I take a derivative to the A, and this part won't control or contribute to any of the derivative. So this we can rule out. So in this case, we can write Y partial derivative to B will be equal to A. In the case that C, D, E, F is not related to A, okay? So that's what partial derivative means. Any question? Confusions? No? Okay. So basically we want to say that when we apply this partial derivative, we can get what the G, H, entropy for relation, how they relate to each other. So the solutions, before we mix it, your your G is N number of moles times each of them has the unit free energy of Ga plus your solvent B and times units. So we can write it as sum of Ni times Gi, and same way we can write that. So the mixing can be simplified down further down to here. Yeah.
Is that Ga times the moles the same as the lowercase ga up top?
Are you referring here?
Yeah, that G compared
Yeah,
to Ga.
yeah. But here, sometimes we write an average or per unit size using a straight line on the top.
Okay.
So let's use some example. So,
Can you go back to the previous slide?
yes.
What is the summation that's happening?
Summation is basically means Ni, Hi, so I can be any number, right? So we usually return this as summation.
Component.
So it could be N1 times H1 plus N2 times H2, so each component. We return as a summation of solution. If you mix in two, that will be N1 H1 plus N2 H2. If you have more components, then it's more a general way we write about how much components in the system.
And what does the bar over the letters mean?
Oh, that's basically average.
Okay.
So you can think about what is the free energy per mole. Does that make sense? Like unit mole energy.
There's a lot of molecules in each mole.
Yeah. So if you how many energy per mole times how many moles you have will be equal to, the energy your system has.
Okay. Can you stay on this for just a second so we
Sure.
can get the equations down?
Yeah. We can take a pause. No problem. Daniel.
In the index for the partial derivative
Yeah.
is P.
Which one?
In the subscript for the partial derivatives,
Uh-huh.
you got T, P. What is the P?
TP, there's no B, right? There's temperature, pressure. At the constant temperature, pressure, then when Ni is not equal to Nj, you can do partial derivative. Okay, everybody has noted down? Okay, I see Amy is still writing. Let's give her a little bit time. Take it easy. Then in the next slide, we will give an example. Yeah, I know thermodynamics is a little bit abstract, so the first lecture we can take as much time as needed to familiarize what is HS and delta G before we dive into more complex. Okay, so this would be example. let's take a read of the question. So if we have this amount of polystyrene at this molecular weight or molar mass, so this is basically molecular weight, is added to this amount of toluene, it's basically polystyrene dissolved toluene. The resulting solution has what is molar volume of polystyrene in the solution. So it asks you about what is partial molar volume. So what is molar volume? We haven't chatted about that a lot. Molar volume is basically how much per mole of your polymer has a certain volume. So we can calculate it based on volume of polystyrene equals to volume, take a partial derivative on how many moles at a constant temperature, pressure, and mole of toluene in this case. There was a code transfer error. This should be toluene, okay? And delta V, we can calculate how much volume change before and after mixing. So this would be after mixing, how much toluene plus polymer minus just toluene only. And this gives you what is volume change. And this gives you how much molar of your polystyrene we have. We can simply use the mass divided by molecular weight. So how heavy they are divided by how much. This would be how much 1 mole of polystyrene weighs. This will give you this number. So this tells you how much mole we have. If you take a derivative, so you use division, VPS is partial derivative V divided by PS, which transfer to that. You can get partial molar for polystyrene. Pretty simple. Now the other part is we want to also get how much each chain has. So polystyrene, we can calculate degree of polymerization based on mass divided by monomer molecular weight. That will give you how much size of your polystyrene has, dP. So lastly, we did one more calculation is if we use VPS divided by how many repeating units, we can get this parameter called VPS volume of per polystyrene's repeating units. So how much repeating units takes up the volume? This will be the total volume of your polystyrene divided by dP. Imagine your chain has a certain length, takes up for a certain volume. If you reduce it by how many repeating units, you can calculate this parameter is what we want. So that's what the volume of the polystyrene per repeating units. And that's important because later we will see when we mix in different polymers, we want to use the lattice series. And in the lattice series, it's very important we know how much volume it takes between a polystyrene versus let's say a toluene when you mix it. Okay? I see quite a few confusion faces. So ask questions, please. Amy, please.
I still don't understand what the volume PS is.
So the volume of PS we can get based on, so we want to see, let's put it this way. First, let's talk about why we need this parameter. We want to get, think about this polystyrene chain. When we mixed with the solvent would represent these molecular. When we mix them, we need to consider thermodynamics and entropy. Thermodynamics is easy, but entropy is a little bit hard because we need to consider the size of your polymer versus the size of your solvent. So we can develop appropriate dimension of these two. So how do we know the size of this polymer? instead of using what we talked about conformation, we can just use partial volume. We can talk about volume or the size of the polymer versus the volume of the solvent. Okay? So that's what we are doing here. We are trying to see how big the polymer are, and we want to see how much dP within a degree of polymerization, how much this volume this one takes. So we took 2 steps. We first calculate how much total volume for the polymer. Then we divide by what is dP. So we'll tell you what repeating units volume. That's what we did here. So total volume is given by how much volume you have as a polystyrene divided by how much amount of polystyrene you have. So that's the volume per polystyrene chain, or per mole of polystyrene chain, not per units of polystyrene chain. Yeah?
You have 2.28 cubic centimeters per gram. Would it be 2.28? How'd you get? Oh, did you just use density
Yeah.
to get?
Mm-hmm.
Okay.
Can you say those thoughts out loud?
It's jumbled.
Okay.
No, I can help.
Did you?
So he asked, where does this come from?
Right.
Yeah.
So this is basically based on the specific volume.
You're right.
And what is specific volume?
Specific volume is how much grams of polystyrene it has. A gram and takes what volume it has.
It's inverse of density.
Yeah.
Mm-hmm. But that will depend on how you process it. But you can use this as an example that how we can learn about specific volume. So now coming back to here, I want to dwell a little bit longer. So why we need to know how big one PS occupies? Because in the next lecture we're going to talk about lattice theory. And I'll give you a brief introduction about what is lattice theory is. Okay, let's start a little bit that. That will help you guys understand it better. So let me move to a bit of that. That will help you guys understand a bit. So I'll talk 10 minutes on this part. So when we think about mixing, let's go take one step back, talk about polymer dissolved in solution. Let's talk about something very simple is, how about we mix 2 solvents together? And when we mix in solvents, we just have a better and much simpler way to calculate what is delta G, delta H, and delta S. And one of the way we need to calculate is called regular solution theory. So what does this example means is when we have, I'm drawing 2 grids of 3 by 3, then I have a grids of 3 by 6. So imagine this would be the volume that 1 mole of your polymer would take. And in the solvent, we need to draw this lattice because it helps us to visualize how molecular mix. So let me use 2 different colors to show you. If we have, this would represent toluene. When we're trying to mix toluene with hexane, let's use cross in this case. So we would have a beaker of toluene and a beaker of hexane. And each of them is represented by these 9 symbols. It can be a square, it can be a circle, or it can be a check mark. So in case of solvents, that's very easy because we assumed that solvents will take up equal volume. But now imagine when I mix a toluene with another polymer. Let's just draw it here. So how much volume that one polymer would take is the question. So how do we know? Because when we mix them, we think these imaginary lattice happens in the solvents. So we just fill in the lattice, simulate the mixing behavior. So I can put it randomly, try to be randomly 1, 2, 3, 4, 5, 9, 1, 2, 3, 4. I'll take 2 more. So this would be representing a mixing behavior when you have these 2 solvents mixed, right? So we can calculate what is the delta G based on what is the G for mixed, what is G for solvent toluene, and what is G for solvent hexane. So we just need to calculate delta G based on G mix minus G solvent. We should not call it solvent. Let's just call it toluene and G hexane. Okay. So using this type of diagram, we will be able to calculate what is the delta G and delta H difference. So in the solvent, we assume the toluene and hexane, each of them has the same size, the bulkiness, and each of them occupies 1 lattice. Lattice means one of these check box. But when we have polymer mixed with solvent, we can't assume a solvent molecule takes up the same volume. Let's say this is polymer. It doesn't make sense, right? The volume for a polymer will be much bigger than the solution molecular. So the size of toluene, imagine it will be much, much smaller than a size of a single polymer chain. So in the lattice theory, we typically actually draw polymer as an example of these connected lines. So this would represent one polymer has a degree of polymerization that is long enough that occupies 1, 2, 3, 4, 5 lattice. And imagine that your polymerization goes on, it will occupy further and longer lattice. So it's very important when we using the lattice theory or Flory-Hagen theory to understand how big or bulky your polystyrene is versus what is the solvent size. So that's why we need to do a little bit of calculation of the molar volume of your solvent versus molar volume of your polymer. So at the end of the day, when we develop this Flory-Hagen theory, we need to know how many lattice that your polymer would occupy. Okay? So now coming back to, we did a little bit diversion to talk about molar volume, but coming back to the delta G related to the mixing process, in the next lecture we're just going to focusing on the solvents. When we mix in solvents, how do we calculate this delta H difference and delta S difference? So we need to calculate those 2 parameters so that we can predict if those 2 will mixed or not and come back to delta G. So I'm going to stop here and then we can pick that up next lecture when we first talk about how to calculate delta S first, then we can calculate delta H. If we can calculate both, we will be able to predict mixture or not. Okay? So a little bit background for the delta S is we're gonna first calculate entropy, and it's not that hard to calculate entropy. So don't be too scared when you hear about entropy and how to calculate. It's related to the number of different states that your lattice is gonna adopt. So we're gonna walk everybody through how to calculate the delta S first. It's actually a value you can get, how much randomness goes up in the system. And then we will calculate what the delta H. Using these two examples, and we will have a few homeworks that can help everybody understand solution mixing first. Okay, just solvents. And the reason we picked the solvent is it's easy. We can make a few assumptions that solvent has the same unit size, so we only need to worry about how to fill solvent within a model box. Instead of worrying about you have to force a chain, which has connectivities and other challenges will be associated. But solution theory and Flory-Huggins theory are highly related. Once you learn one, the second one is much easier. Pretty much like freely joined chain model versus some of the other more advanced one. So, any questions so far? Okay, you guys survived the most challenging part. I always felt the introduction to thermodynamics is one of the challenging one, because for a lot of you, if you're coming with chemistry background and never heard about delta H, delta S, it's quite abstract. So don't be afraid. We're gonna make abstract items to be more specific one when we move along the courses. Okay, with that, I'm gonna wrap up the class, and we can meet again later this week.